Mr. Who, I think you're muted.
You just okay. Sorry. Someone's judging me for where I went to high school. Oh my gosh. There's any high school. There's good. There's people who are nice, and then people who are mean. I think that's such a that's hurtful. Anyways, I'll deal with you later. Okay. Okay. Yes, I know you. Where you couldn't hear me. Okay, it's okay. I was just bantering. Okay. So what does a year measure? So a year actually measures how long it takes for the Earth to go around the sun once. Which is 365.24 days. So this is an actual measurement. Most of the time, a lot of the times we sort of assume, a lot of times we sort of assume that that the that that it's like just an arbitrary thing, but it's actually like we actually it's actually how long it takes for the Earth to go around the sun, and it's actually 365.24 days. So that's why we have leap years, because every 4 years that 0.24 days adds up to another day. So which is why we need to have a leap year. Um, so now the thing is, a year is just a measurement of the revolution time of the Earth around the sun. We can also measure different kinds of revolutions. So we can measure how long it takes for a clock to go around to go around. So for example, the minute hand has a revolution time of 60. Well, I mean, it takes 60 minutes for the minute hand to complete a loop, and it takes 60 seconds for the second hand to complete a loop. So that's another way we can measure, another thing that we can measure the revolution time of. We can also measure how the revolution time of a merry-go-round, so how long it takes for a merry-go-round to complete a revolution. So there's a lot of different ways we can measure the revolution of different objects. So the question I pose to you is, how can we measure the revolution time of any object? So how do we measure the revolution time of an object? If I just said this person is driving donuts in the parking lot, how would you measure their revolution time? So I'm gonna put you in your groups here, and I want to see if you guys can come up with some explanation for how you might measure the revolution time of an object. All right, Zoe. Okay, so in terms of how do we measure revolution times of stuff, in general, what you might have discussed is something like this. In general, right, if I can figure out how much distance I need to cover, and if I know how fast I am traveling at a certain speed, right, I can sort of take the two and then divide them to get a time. So in general, to measure how long it takes to travel a certain straight line, I can just take my distance and I can divide it by my speed, and I'll get a time for that. So the thing about circles is that they are actually straight lines that are curved. So um, imagine if you took a straight line and then you bent it, and that's what a circle is. So they literally are straight lines that are just curved. So in terms of figuring out how long it takes to go around a circle, it's the same idea. If I know how much distance I need to cover, and if I know how fast I'm going, I can divide the two to figure out how long it takes for me to go around the circle. So right, the general principle is the same, right? The amount of time it takes is just going to be my amount of distance I need to cover divided by the speed I'm going, and and then that will give me my my amount of my revolution time, I guess. Now the question is, how can we measure the distance around a circle, and how would we measure the speed around a circle? The speed around a circle is a little bit trickier, but I think that measuring the distance around a circle, I think, is very, very. Oh gosh, my slides keep disappearing. You're supposed to tell me, Zoe, if my slides aren't showing. That's literally, I do too, but it's not. But if you can't see what I'm talking about, then it's kind of pointless. So, I know. So what I want you to do is I want you to think about, how do you measure the distance around a circle? How do we do that? Maybe a couple of minutes. How do we measure the distance around a circle? So the measuring the speed around a circle is a little bit harder, but in terms of the measuring the distance around a circle, that's literally what we call the circumference. And the circumference we can calculate by taking 2 times pi times r. And we can use that to figure out the distance around a circle. In terms of the speed around a circle, this is actually something different. This is actually called something called angular velocity, which I don't think I'll cover right now. I don't think I will cover because it's a little bit more complicated. But measuring the distance around a circle, this is very important. It's just 2 pi r. Because now that we know the distance around a circle, we can use that to figure out how long it takes for me to go around said circle. So this is where you need to figure out, this is where we start calculating, start doing some math. So this is very important. You should write it down. So write it down. So the period revolution is basically how long it takes to go around a circle. And we use the variable t to calculate we use the variable t to express the period of revolution. To calculate the period, the amount of time it takes to go around a circle, we basically just take the distance and divide it by the speed. So the distance around a circle is just the circumference, 2 pi r. And the speed is just our velocity. So if we take the down to distance I have, 2 pi r, and I divide it by my velocity, which is v, that'll give me how long it takes to go around said circle, which is my period t. So period, the letter t, is how long it takes to go around a circle. In terms of orbits, what I'll call it is an orbital period, which is basically how long it takes for a planet to orbit around the sun. And I use the variable t to express that. And we can calculate t just using the following formula, which is the distance around a circle, 2 pi r, and divided by velocity, which is v. Okay, so someone brought up that this technically wouldn't work for an ellipse, and you're absolutely right. The thing is, what we're going to do is, because this is, we are going to, well, first off, the amount of well, the technical amount of terms, the amount of eccentricity that a planet has, it's actually, the orbits are actually not very elliptical. Like I think Venus's orbit is almost perfectly circular. So the amount of ellipsiness, I guess, that the planets have is not enough. It's not very significant. So we can approximate this. So we can use this formula here to still approximate the period of a planet. So it is not perfect, as you're 100% correct. So yeah, but this is an approximation. A lot of times in science, we use approximations for things. We assume that things are roughly this, just because it makes our life easier. For example, a common joke in physics, you assume everything is a spherical cow, which because spheres are easy to work with. Or you assume that things are just a singular point, because it makes things easier to work with. So it's the same idea here. It's just easier to work with. But the general principle still holds. And we're going to use this to establish a relationship, which is still generally true. So yes, you are correct that it's not technically the most accurate, but it's accurate enough for our purposes. There. Okay, so I'm sorry, I was muted. So the next thing I'm going to do is a little bit more complicated. I really can't say much more than you have to trust me on this, because I'm a little bit more complicated, and honestly, like where this comes from is a little bit more complicated. So you're just gonna have to trust me on this. Not that you don't already trust me. I'm a very trustworthy person. Um, so this is what we call Kepler's second law of planetary motion. This relates to how much distance a planet is covering, essentially how much area a planet is covering as it goes around a star. And the law states that a planet orbiting a star will cover equal amounts of areas during equal amounts of time. So if my planet is starting at this point right here, and it's moving to this point in 1 month, this amount of area is going to be the same as this area if this part also takes 1 month. So as long as it takes, the same amount of time, the amount of area the planet covers is the same each way. So how does this work? Well, if you look at these two, I guess the true triangle-ish thing, right? When it's farther away from the sun, the height of this triangle, in other words, how far the planet is from the sun, is going to be very big. But the amount of distance it covers around the orbit is not very big. So it's like a tall height, skinny base. So when you combine the two, you get a triangle. When it's closer to the sun, though, it has a wider base because it covered more distance, but it has a shorter height. So when you combine the two, it's going to roughly balance out. So the general idea is basically, right, all these areas are going to be the same as long as the planet covers that time in the same covers that as long as the planet is keeping the same consistent time interval for each area. So we're going to use this to sort of make some predictions about how the planet's make some predictions about the planet's motion as it goes around the star. To also give you a visual of this might look like, I have a little simulation here. Where is it? Here it is. Okay. Where this sort of maps out different areas as the planet goes around, and each one of these areas is the same as each other. As the planet goes around the sun, right, it's mapping out different areas, and the amount of time that it spends during each area is the same, and the area size is the same as well. Which means that the height and width may vary, but the overall size of the area remains the same. Okay, so that's what we call Kepler's second law. It's probably one of the more conceptual ones, but we will use it later on. A more practical, pragmatic one, I guess, is what we call Kepler's third law. um, which with this one actually deals with relationships between quantities. So Kepler's third law relates the period squared to the uh, semi-major axis cubed. So you remember what a semi-major axis is? You remember some? Okay, I'll go over it one more time. I feel like that might be helpful. Okay, so Kepler's third law relates the period squared to the semi-major axis of the orbit. So what is the semi-major axis? Let's go back and review. So the thing is, the reason why we use the term semi-major axis is because planetary ellipse orbits are elliptical. So which means that we can't use the term radius and we can't use the term diameter because there's no such thing, right? The widths of it will change. Now, the thing about an ellipse and any sort of oval is that there are sort of two parts of it, I guess. There is sort of the skinny part, and then there's sort of the wider part. So the wider part is what we call the major axis. We call it major because major is big. We call this the smaller side the minor axis because it's not as big. So when we're saying, okay, I want to measure the major axis length, you're just measuring basically the length of one far edge of the. Oh, this keeps disappearing. You're measuring one far edge of the ellipse to the close edge. And then if I'm measuring the semi-major axis, I'm actually only measuring the middle to one of these far edges. So that's why it's called semi-major, because semi means like part, so it means like halfway. Major axis means the big side. So when we measure distances when we measure planetary distances, we actually measure the semi-major axis, basically how far is the planet away from the middle of the ellipse, essentially. So this is very important because we use semi-major axes to measure planetary distances. So when we're comparing the radius cubed to the period squared, we're actually comparing not the radius, the semi-major axis cubed. So this relationship states that basically the period of revolution squared is proportional to the radius cubed. If you've never done proportionalities before, this is definitely going to be pretty confusing. So I'm going to try my very best to explain it, but I've had limited success so far. The idea is any changes in the radius, the distance of an object from the sun, any changes in that is going to be proportional to the amount of change that the orbital period will have. And then how proportional that is a r cubed to t squared relationship. So basically, when I'm going to take whatever changes I have in my orbital distance, my semi-major axis, my r, any changes in that, I'm going to cube that, and then I'm going to take the square root of that to get how much my orbital period changes. Okay, so to give you an idea of what I actually mean by this, I think I'm going to try my best to do an example in a second. But for now, I just want you to make some very general predictions here. How would the orbital period change as we get farther away from the sun? And what if we get closer? So remember that our orbital period, t squared, is proportional to my orbital distance, my semi-major axis cubed. So I want you to make a prediction. How would the orbital period change if, as my distance from the sun gets bigger? How would my orbital period change if my distance from the sun gets closer? And then vice versa. If the amount of time it takes for me to revolve around the sun is increasing, how would my orbital distance change? And what if my orbital period was decreasing? So basically, I want you to think about what happens if one is changing and the other one is changing. And I want you to try to come up with some predictions. Yeah. Okay, so so in terms of how do these change, so what we're looking at the relationship that is the period squared proportional to the radius cube, I keep saying the radius. That's actually a bit of a misnomer. This r is the semi-major axis. So the thing is, right? It's as one of these increases. So if r is getting bigger, t is also going to get bigger, which means that basically as I'm getting farther away from the sun, as my r is getting bigger, as my semi-major axis is increasing, my period of revolution is also going to increase, which basically means the farther I'm getting away from the sun, the more time it takes for me to revolve around the sun. Vice versa, the closer I'm getting to the sun, the shorter my orbital period is, which means that the faster it's going to take for me to, the less time it's going to take for me to revolve around the sun. So the planet Mercury has the fastest orbital time in our solar system because it's the closest, whereas Neptune and Pluto have much slower orbital times because they're much farther away from the sun. And so we look at the opposite, right? If it takes us more time to revolve around the sun, that means we're getting farther away from the sun. If our orbital period is decreasing, that means we're getting closer to the sun. So basically, it's sort of as one changes, the other one also changes in the same direction. What gets really tricky about this, though, is that it's not a one-to-one relationship. What do I mean by that? What I mean by that is if the radius of my semi-major axis doubles, so if my distance from the sun doubles, the period does not double. It's a cubed to squared relationship. So basically, you have to take the ratio of the changes, and you have to cube that, and then you have to take the square root of that to get how much the period changes. I'm going to do a practice problem with that. I'm going to do an example problem with that first, because it's really hard. It's really hard to explain even with a practice problem. So I'm going to do my very best though, because it's tough to explain. So this is a lot easier. So before I do the example problem, I'm first going to talk about the units we're going to use for a lot of this unit. So in space, we don't really use meters because meters is kind of like stupid because meters are really small. No, meters are really small. Space is really big. So when you consider that Earth is 93 million miles away from the sun, and each mile is what, 1,700 meters or something. So you take 93 million multiplied by 1,700, and that is what, 9.93 billion? Dude, okay, so 93 billion meters from the Earth to the sun, maybe something like that. Okay, so I could say that, or I could just say that's 1 AU. So I think it's more efficient. So basically, in astronomy, and we often use the unit AU, which means astronomical unit, and we use that to measure distances within a solar system. We also use some other units such as parsecs and light years, but those are usually for much bigger distances. Usually within a solar system, you usually use AU. The way we set our AU is that 1 AU is exactly how far the Earth is from the sun. So Earth is exactly 1 AU from the sun. That's what we calibrated our units as 1 AU as being that. So Mars, for example, is 1.52 AUs from the sun, meaning that Mars is 1.52 times farther away from the sun compared to the Earth. Similarly, Venus is 0.72 AU from the sun, which means that Venus is 0.72 times closer to the sun compared to the Earth. So Mars is farther away from the sun. It's about 1.52 times farther away, and that's because Mars is 1.52 AU from the sun. Venus is 0.72 AUs away from the sun, which means that Venus is closer to the sun than Earth by a little bit. Yeah, so the general idea is basically AUs is the units we use to measure distances in space. 1 AU is just how far the Earth is away from the sun. And so if something is 2 AUs away, it means it's twice as far away from the sun as the Earth is. So we're now going to do an example problem with Kepler's third law here. And what we're going to do is we're going to use an example planet. This planet has no name. You guys should give it a name. Okay, so I'm gonna give this planet a name. I'm gonna call this planet Endor after episode 6 of Star Wars. If you haven't watched that movie, then you get a 0 in the class. Okay, Zoe, I was looking, Armand thankfully gave me a nod. Zoe just ignored me completely. Disrespectful. Yeah, but he didn't give me a nod though. You know what? You know what? Fine. I don't need my positive validation from you. Okay, so basically, next reading problem, if Endor is 2 times farther away from the sun compared to the Earth, how long would it take for Endor to revolve around the sun? So here's I'm going to set up the problem here. Basically, in order for us to do this problem, we're going to need to use Kepler's third law. We're going to need to use Kepler's third law, which is one that is period squared is going to be proportional to my semi-major axis. So I'm just going to write down the things we know. So Earth has a semi-major axis of 1 AU. It's R being semi-major axis. And then Earth has an orbital period of 1 year. Orbital period meaning how long it takes to orbit around the sun. That's Earth. We want to figure out the same thing, but for Endor. Endor has a semi-major axis of 2 AUs. That's how far away it is from the sun, and that's just given to us. And I need to figure out how long does it take for Endor to orbit around the sun. But we don't know this. That's what we need to figure out. Okay, so this is where we're going to need to use Kepler's third law here. The idea is basically the ratio of the. We're going to be looking at a lot of ratios eventually. We're looking at the ratio of I guess, distances. We're comparing this to the ratio of periods. So the general principle is I want to compare the ratio of distances between Endor and the Earth. And that cube is going to be roughly equal to the ratio of the periods between Endor and Earth squared. I'm looking at ratios here. And the ratio of distances is basically how far is Endor relative to that of Earth. So Endor is 2 AUs away. Earth is 1 AU away. So the ratio is 2. So this ratio cube is going to be proportional of the ratio of Endor to Earth. We don't know what Endor's period is, but we know that the ratio squared is going to be proportional to the ratio of Earth's, of this ratio cube. So we're essentially solving this equation. We're basically essentially solving this. So 2 over 1 is just 2. 2 cubed is 8. Right, because 2 cubed is 2 times 2 times 2, which is 8. 8 is going to equal t squared 1, which is just t squared. So which means that my t should be square root of 8. And how long, we're doing, and our period is usually measured in years. So what this means is that Endor orbits Earth in square root of 8. Endor orbits the sun in square root of 8 years, which is, I believe, like 2.7, I think, if I remember correctly. By 2.8. Okay. So if Endor is 2 AUs away from the sun, which basically means that Endor is twice as far from the sun as the Earth is, it actually takes 2.83 years to orbit the sun. Not what we might expect to be 2 years. It's actually 2.83. And the way we got 2.83 is we took the ratio of Endor's orbital distance, which is, so Endor is 2 AUs away, Earth is 1 AU away. So we take the ratio of these two, 2 over 1. We're going to cube that ratio. And then we're going to set that equal to the ratio of their periods. And the ratio of the periods is Endor's period, which we don't know. I left it as t. And we left that in comparison to Earth's period, which was 1 year. So this ratio cubed is going to equal this ratio squared. Then I just solved it. So I get that t squared is equal to 8 And so that means that t is equal to square root of 8. Okay, so that's one example problem. I think I'm going to do one more to just give us some practice for this. Or I have you do the practice problem by yourself. So this time I'm going to, let's say, instead of using annual, I'm going to use the planet. I'm going to use the planet Hoth. That's so fun. And let's say that Hoth is 3 AUs away from the sun. And once again, we're going to create a frequency period. So now we're looking at a second planet here, Hoth. This is 3 times as far away from the sun as Earth, and I want to figure out how long does it take to revolve around the sun. So the idea is the same, right? I want to take the ratio of Hoth's distance to Earth. So Hoth is 3 AUs away, Earth is 1 AU away. So I'm going to take the ratio of this 3 to 1. I'm going to cube this ratio, and I'm going to set this equal to the ratio of the orbital periods. We don't know what Hoth's orbital period is. But we do know what Earth is, and Earth is 1. So I'm going to set these equal to each other. And so what I get here is that 3 over 1 is 3. 3 cubed is 27. And then t over 1 squared is just t squared. So t squared should equal 27. Think of the square root of both sides. And so what I get is that my orbital period here should equal roughly 5.2 years. Okay, so that's more or less the gist of it, right? You got to take the ratios of things. Yeah. So when we're working with Earth, I think the ratios are. I think so far, I think this is probably the most simple way I think I've made it so far. But the idea is the same. You take the ratio of the distances, cube that ratio, and then you compare it to the ratio of the periods squared. So I think that's this is the best way I found of explaining it so far. But what I'm going to do now is I'm going to let you do a couple practice problems, and then we'll see what we can get. Okay. So in terms of the 2 practice problems, Jupiter is 5.2 AUs away from the sun. What would Jupiter's orbital period be? And then the second one is Mercury has an orbital period of 0.24 years. What would Mercury's orbital radius be? Or not orbital radius, orbital distance be? So these are your 2 practice problems. So I'm going to give you the rest of the class to work on these, and then I'll go around and see how people are doing. So yeah, whenever you wrote everything written down, you can join your room and then see if you can do it. You can do it. Yeah. Okay, so we're going to continue this on next week on Tuesday. So yep, I don't have anything else for you guys today, so I'll see you guys on Tuesday.
Thank you.
Thanks, Mr.
Thank
Ho.
you.
Thank you. Thank you.